on the easy side. 6.5b is the one I left over last time, proving identity, and 7.1 to 7.3. 7.1 to 7.3 is application of radian into what we have learned, okay, and using radian to find arc length and area, linear velocity, angular velocity. Now, those material, including this 6.5, actually a material that we have learned, you have learned in trigonometry. Well, the proving identities especially, more or less we have learned earlier on last Thursday. That's basically simplifying expression. Now, what is proving identity? Now, proving identity is when we have an expression equals to another expression, and we try to prove that these two expressions are equal. Now, the way we treat this kind of proving identity most of the time is thinking of simplifying expression. So you look at these two expressions here, expression 1, expression 2, which is more complicated, okay? And we will prove this identity by simplifying a more complicated expression to the simpler one. Now, suppose, for example, suppose expression 1 is the more complicated one. So I will move from expression 1, okay, use this identity, use that identity, use this kind of algebra, that kind of algebra, and then we simplify from left-hand side to right-hand side. Now, structure, okay? When I ask you to prove this identity, okay, suppose we'll prove from left-hand side to right-hand side, then your first line should look like this. Your first line should look like this. So your first line is the proof, and then the direction of the proof. Okay, in this case, we'll prove from left to right. Now, if you prove from left to right, then you will write LHS first, that stands for left-hand side, and equals to expression 1. In this case, the expression that you consider more complicated. Okay, now, and then we simplify. Now, when you simplify, do one step per line, okay? Don't try to do too many things in one step, okay? Please don't try to do too many things in one step. Of course, I will penalize you if I see that you skip too many steps, okay? But what usually happens is this, the steps that you skip, very likely the step that you don't know what to write. The way you think is it's too simple such that you don't need to write it. But what I found in my teaching career, and also I learned this from my teacher once said this, that the reason you cannot write it down because you cannot even write it down in your mind. Okay, if you can't even write it down in your mind, then you won't be able to write it down on paper. Okay, that's the way she said it. At first, I didn't really believe it until later on when I start teaching. Then I realized that some students, they say they did it mentally, but when you ask them to write it down, they can't write it down. Okay, such that the phrase "I did it mentally," that sentence is actually just a mask to cover or to deceive themselves of what they don't know. In this case, they don't know how to write. Okay, so please be aware with that, with your the reason why you skip steps. Okay, if there's any point that you wonder, like, you know what, do I need to write this, Thomas? Do I need to write this? If you ever have that question, then write it down. Okay, when it comes to proving, if you wonder, do I need to write this detail? If you ever think that way, then write it down. Okay, and I can say that when it comes to proving, I myself don't like proving at the beginning. Okay, too bad. I learned proving since very, very early, and we start doing a lot more proving when I did from my second year, basically from my sophomore year to my senior year, basically we did proofing a lot. Okay, so get used to it though. Okay, get used to it. Now, after you simplify, eventually you will reach example 2. Okay, now then the closing remark, the last line of your proof will be equals to right hand side. Because you proof from left to right, right? So after you reach example 2, which is your right hand side, you say equals to right hand side, and then you close it. Okay, now this box, this square that we fill up there means the end of the proof. Okay, now in the past we use QED for the end of the proof. QED stands for Quod erat demonstrandum, which means therefore it is shown. Basically, that's a statement saying that I'm done with the proof. Okay, now I will show you some examples, especially in the first one is to teach you the structure. I want you to write your proof this way. Okay, I want you to write your proof this way. I want you to write your proof this way. Okay, now of course in this example I start from left hand side. You may start from the right hand side if you think right hand side is more complicated. Okay, now let's start. Let's see example 1. Proof. I would like to pick question from the book right away. Proof. Oops. Proof. Let's say proof number 18. Number 18 on 6.5. Tangent beta sine beta equals to secant beta minus cosine beta. Now, what you need to do is first think about which of these two expressions, the one on the left or the one on the right, is more complicated. Now, the definition of more complicated is actually quite ambiguous because it really depends on how mature you are mathematically. But most of the case, on the other hand, you can actually prove in either direction. Okay. Now, suppose I want to prove from the left to right. So proof, my first line will look like this if I want to prove from left to right. Left to right, that's the direction of the proof. Left hand side equals to tangent beta sine beta. Okay, no computation, nothing. It's just administration, formality. Okay, now then from there we do the algebra. So for example, usually because I have tangent sine and in my resulting expression I have secant cosecant, let's just change this into sine cosine style. Right, so tangent equals to sine over cosine. Now then this is equals to sine squared beta over cosine beta. Now, any idea how to get there?
You're going to change sine squared beta to 1 minus cosine squared beta.
Okay, 1 minus cosine squared beta over cosine beta, and then?
And then you separate the fractions into 1 over.
Okay, so 1 over cosine beta minus cosine squared beta over cosine beta. Right, the first term is secant beta. The second term is cosine beta, which is our right hand side. So that's the end of the proof. Okay, now notice that when I do the proofing, my equal signs, as much as possible, make it straight, just like the way you solve your equation. The equal sign, if possible, make it straight. That's one. Second, notice that one step to the next step, I break it down into very little steps, such that every reader should be able to understand it. Now, keep in mind, the one who will grade you will be your instructor, right? I will be the one grading you. But when I grade you, I will see how can you break the steps down into a very simple step. Okay, so try your best not to skip too many steps. Well, there are some steps actually quite simple, I can understand, but also take a look on the number of points I assign for that question. Okay, if for this example here, I give you only 3 points, yeah, then I think you can skip 1 or 2 steps from here. But if I give you 7 steps, 7 points from here, then it won't be short. Okay, it won't be short if there are 7 points or 6 points.
No,
Now,
what if we run out of space on the test?
Then you write it on another paper.
Okay.
Professor?
Yes? Yes, Yuma? Hello? Hello? Yuma, you
Professor?
have a question? Yes,
What if we have like redundant steps? Would you deduct points?
Redundant steps?
Like what if we like went into like a loop, or like if we have like unnecessary steps?
I don't need to deduct you points. You already waste your time there.
Okay.
Right? Okay, you already waste your time there. And you will see that you don't have enough space and you won't be that. See what happens is this. The fact that you get into redundant cycle, like A to B, and then you go back to A, and then you go back to B again. That's because you don't have plan. And when you do proofing, more or less, you need to have some planning in mind. You should be able to see a couple steps ahead. Okay, now using this example 1, I will also prove the other direction. I want to show you that this identity actually be proven, possibly proven from one side to the other side. So secant beta minus cosine beta. Secant is 1 over cosine beta. Okay, cosine beta, make it over 1 here. And then I do LCD, is it right? My LCD is cosine beta. So multiply the top and the bottom by cosine beta. This will be cosine squared beta. This is cosine beta. Now, once they have LCD, I can put them in the same fraction. This is 1 minus cosine squared beta over cosine beta. That's the LCD. Then on the top, I get sine squared beta over cosine beta. Then from here, I rewrite it in sine beta over cosine beta times sine beta. Now, I understand that some of you may say, Thomas, do we really need to write that last step, If I were you, I'll do. Okay. Yeah. Even though I have to admit that I think from here to here is actually quite obvious. You see what I mean? Some of you can just see it right away. But why I tell you to write it anyway? Because you don't know my mood when I do grading. I mean, to be honest with you. Yeah, to be honest with you, I try my best to have my mood really good when I do my grading. Okay, but it just takes like 1 or 2 students kind of skip steps here and there. And then when you are the one skipping steps, I deduct your point. You see, I try to avoid that from happening. But the thing is, I have to admit, it's kind of hard to avoid being biased and be reasonable when I do grading. And you purposely kind of like try to skip steps. Okay, if I see that you are someone who like to skip steps here and there, then it doesn't take this one to pick me to kind of like tick me off. Okay, other part will already pick me off. Okay. Yeah, but well, anyway, this is for example one. I would like to do more questions, and these more questions also represent some other technique. Now here, basically the main point is I want, from this example one, I show you how to show the proof, the structure, okay? The first line will be proof, direction of the proof, and then left-hand side, and then what you see on the left-hand side, or the direction of proof, right-hand side, what you have on the right-hand side, okay? And then on your final two steps should be the other side, okay, equals to right-hand side in this case, close it, or the other side equals to left-hand side, close it. Okay, so your proof should consist at least four lines, at least four lines. The yellow line, one of the yellow line, two of the blue line, and one intermediate steps here, something in the middle. Okay, at least four lines. Now, also from example one, I showed you that if I prove it from left to right, one of the key steps is to rewrite tangent. If we have sine, cosine, tangent, secant, too many functions at once, then I break them down into sine, cosine. That's actually a very basic technique. Okay, and then somewhere in between, I use law of Pythagorean identity, right? Now, if I start from the right-hand side, the new thing is that I do LCD so that I can put them together. Okay, and when I put them together, hey, you know what? We have a trig identity, Pythagorean identity to apply. Now, other technique, example two, let me pick question number, I saw a good one earlier, number 26. I think, in fact, number 26 is a question that I have asked at least twice. At least twice. I don't even remember if I asked them in Precalculus or in my trigonometry, but this is basically a very good question. Prove that sine B over 1 plus cosine B plus 1 plus cosine B over sine B equals to 2 cosecant B. 2 cosecant. Now, this one is clear that we will prove from left to right. Okay, because the left-hand side is clearly more complicated. I'll prove from left to right. Left-hand side equals to whatever you see on the left-hand side, that's what you copy down. And that's your 1 point. That's your 1 point. Now, I will show you two different methods to prove this. Both of them start from the left-hand side, okay? And the reason I show you more than one method is because the main purpose of proving is not only that you know how to use the formulas that you have, you also see the relationship between those formulas. Okay, there are so many formulas in trigonometry such that if we don't do proving, it's so hard to find relation from one to the other. Okay, again, I myself didn't like proving until much later when I see how proving already equipped me, strengthened me, basically built nerves from one identity to another identity, how all those facts, all those formulas actually related from one to the other. Now, the first method that I will use here, method one, is I will do LCD. Okay, that's what I will do. So I look at these two terms here. What's the LCD?
Sine square.
Huh?
Sine
I have 1 plus cosine B and also sine B. So the LCD will be sine B times 1 plus cosine B. Sine B times 1 plus cosine. Okay, so on the top, I already have sine B. I already have sine B on the top, on the first one. What do I need to multiply by?
1 plus cosine B.
Huh? Oh, I already have 1 plus cosine B at the beginning.
Sine square B.
I need to multiply by another sine B, right? Okay, I need to multiply by another sine B. So on the top, it will be
Sine square B.
sine square B. Okay, now then on the second fraction, I already have sine B. I need to multiply by 1 plus cosine B. Originally, I have 1 plus cosine B, but I need to multiply by another 1 plus cosine B. So I get this. Now put them together. The denominator is sine B 1 plus cosine B. On the numerator, the first numerator is sine squared B. The second numerator, let me just FOIL it right away. Can you FOIL that for me?
1 plus 2 cos B.
1 plus
2 cos B.
plus
Cos B square.
squared B. Now, and then you notice that sine squared theta plus cosine squared theta is
1.
1. I get 1 plus 1 plus 2 cosine B over sine B 1 plus cosine B, which is 1 plus 1 is 2. That's 2 plus 2 cosine B over sine B 1 plus cosine B. What do you think I should do next?
Vector 2.
Vector the 2 out. And you suddenly see something cancel, right? That's 2 over sine B. That's 2 cosecant B. That's our right hand side. That's the end of the proof.
Quick question.
Huh?
So like when we're using the basic trigonometric identities, like how you have the red, the circle, that's how you want us to circle it, right?
No need.
Oh.
No need. You don't need to color it. You don't need to circle it.
Oh.
Yeah, you don't need to color it. You don't need to circle it.
And,
So,
and for like other questions, when we're using like either the basic principles from 1 to 4, do we say that we're going to use it before we use it, or just
no need. I usually write it down, but like for example, what I did here, what I did here is actually basic identity, the second group, the first formula, right? Okay, sine squared theta plus cosine squared theta equals to 1. But I write it there actually for you. If somebody asks me, oh, why is it true? Then the reason is because that identity. Okay, but you don't need to write it. You don't need to write that. You don't need to write this here. You don't need to write it. You don't need to circle it. Okay, I mean, I memorized those formulas. Don't worry about it. I know which formula you use. Okay, I know which formula you use if there's a formula like that. Right? Okay, now if you invent your own formula, then I will circle it and I say why. Right?
Right.
Okay, yeah, so for you to invent a formula, you need to prove that formula. Okay, now your formula may be right though, don't get me wrong, your formula may be right, but if we have never proved that, it's not in our list, then you have to prove that for me. Okay, now the second method, the second method. I will still prove from left to right. So this is sine B over 1 plus cosine B plus 1 plus cosine B over sine B. Now, the other technique I do is, let me move this to the left a bit here so that I have more space. The other technique that I will show you is to multiply by the conjugate. Now, notice that this is already one denominator, the denominator only one term. I have issue with this. There are two terms here. Okay, so what I will do is I will multiply the first term. Oops. I'll multiply the first term, the numerator and denominator of the first term, by the conjugate of its denominator. I multiplied by 1 minus cosine B over 1 minus cosine B. And for the second fraction, I just leave it like that. Okay, now Thomas, why do you do that? Well, because I know when I multiply this guy here, I get difference of squares, right? I get difference of squares, and that's a very nice difference of squares. So on the numerator, I get sine B times 1 minus cosine B. The denominator, I will get
1 minus cosine square B.
1 minus cosine squared B, which we know to be
Sine square B.
sine squared B. Okay, and you see that one of the sine B will cancel, right? And when I cancel, I get 1 minus cosine B over sine B. Notice that all of a sudden we have LCD. Now, because we already have LCD, let's just put them together. 1 minus cosine B plus 1 plus cosine B over sine B. That's 2 over sine B. That's 2 cosecant B. That's the right-hand side. Therefore, the end of the proof.
Quick question.
Mm-hmm.
So when you multiply by the conjugate, I was of the notion that you have to multiply both of them.
What do you mean by both of them?
Because you know, usually when you or did you just change that fraction and I didn't know you could do that. Just multiply one and then not the other. You can do that?
Yeah, we can do that. We have done it. We have done it. Yeah, suppose I have 3 over 4 plus 1 over 8.
Yeah.
What do? You multiply this by 2,
yeah,
and this by 2.
yeah.
That's what I basically did there, right?
Oh, so it's always in relationship to the other fraction. Is that what you? Or you could just.
Well, okay. You can say that it's relationship with other fraction. It could be the case, but the way I see right now is like, you know what? I don't like 2 terms at the bottom.
Okay.
If I can make it 1 minus cosine squared, that happened to be 1 term, sine squared.
Mm-hmm.
You know, okay. And if I get sine squared at the bottom, I can cancel with one of the sine at the top.
Okay.
Right?
Right.
Okay. So even for number 28, I provide you 2 proofs. Would you like to pick one question from here before I move to another section? Between number, let's say between number 27 to number 36.
36.
Number 36, okay. Number 36. Tangent A, tangent B equals to tangent A plus tangent B over cotangent A plus cotangent B. Once I finish writing this problem, I have 4 different ways to show this. So if you want me to show all of them, either we don't have enough time or you will get even more confused. So don't memorize the proof, memorize the principle behind the proof. Which is more complicated here?
Can we do it with this
Right-hand side.
turning tans to sine over cosine?
Yeah, but would you do, which one is more complicated? What direction will you prove this? Left to right or right to left?
Right to left.
Right to left, okay, that's what I have in mind too. Right hand side will be tangent A plus tangent B over cotangent A plus cotangent B. Now, then from here we think about how how would you like to proceed. I know that I think Nona said that convert that to sine and cosine. That's actually a good idea, but that's not the only way though.
You can convert cotangent to tangent.
Yeah, that's actually another way. Okay, so let me do the sine cosine style first. This is, so it should be B. This is cosine A over sine A plus cosine B over sine B. Okay, how would you like to proceed from here?
Common denominator?
Which one?
Oh, for the cosine A and B?
Okay, so for the numerator, the LCD is cosine A cosine B. This is cosine A cosine B. This will be sine A cosine B, and then sine B cosine A. That's for the numerator. Okay, let me color it so that you know what I'm doing. So this guy becomes this guy. Okay, and then later on, this guy here will become what we have the color. Okay. So that will be the LCD for the denominator is sine A, sine B, sine A, sine B, sine A, sine. So on the blue part, what's the numerator of the first term?
Cosine A.
Cosine A sine B
Okay,
and cosine B sine A.
cosine B sine A. Okay. Now then, the reason we did LCD for the numerator and denominator so that we can put them together under one fraction. Okay, so I get on the top sine A cosine B plus sine B cosine A over cosine A cosine B big over cosine A sine B plus cosine B sine A over sine A sine B. Now what?
Is it sine A plus B?
Huh?
Sine A cos B, sine B cos A is equal to sine A plus B?
Yeah, but that's chapter 8 though. You cannot do that
Okay.
yet. You cannot use that yet. Think simple, okay? This is still our yellow one, right? This is our yellow one, and this is our blue one. Okay, a fraction divided by a fraction is the numerator, sine A cosine B plus sine B cosine A over cosine A cosine B multiplied by the reciprocal. Okay, sine A sine B over cosine A sine B plus cosine B sine A. Okay, I multiply by the reciprocal. So this is the numerator divided by, multiplied by the reciprocal. Okay, so then what next?
Can we use the I don't know, we had these formulas like sine A equals to cosine B. Can we just like replace those?
Sine A is not equals to cosine B.
Conjugate.
Well, no, in the formulas that we had from the last video.
What formula?
Like tangent A equals to cotangent B
No, it
That's
is
for the inverse
that's
sign?
yeah, no, that's if A and B are complementary.
Ah, okay, never mind.
Yeah, so we cannot use that one. We don't know if A and B complementary or not here.
conjugate. We can use the conjugate.
Which conjugate?
The conjugate of the blue.
Of the blue?
Yeah, the
But the
bottom.
blue is a fraction. You mean the denominator of the blue?
Yes, the denominator of the blue.
Oh no, I don't think that's what you want to do.
Oh,
No,
Wait, can we
Oh.
write this? Oh wait, never. You know what? I give up. I don't know.
You give up? Okay, you give up too early. Okay, because if you think about it, see, pay attention to detail. What you have here, what you have here is actually exactly the same thing to what you have here. See, sine A cosine B, this part here, sine A cosine B, is this guy, right? And sine B cosine A is this guy. So those two terms, the top left and the bottom right, are exactly the same one. You like cross cancel, why don't you do that? Well, because you don't see it, right? Yeah. Why you don't see it? Because that guy is so ugly. Yeah, ugly people don't deserve any further look. Okay, so no wonder I have hard time to get married. Because nobody wants to look at my ugly face. Yeah. So yes, this is one of the difficulty of making it into sine cosine, and we already have two angles A and B. Okay, so once you make it into sine cosine, then you end up dealing with sine A sine B, cosine A cosine B, and once it gets more terms, then you may not be able to see this red circle here. the red circles you have on the top left and red circles on the bottom right. You don't realize that they are actually the same. But if you realize that they are the same, notice that those ugly people kill each other. Ooh, that's really attack. Okay, ugly people kill each other, then only cute people left. So this is tangent A, tangent B, which is what we want to see on the left-hand side, right? We prove from left, right to left, remember? Okay. Now, I actually like Ney's approach. Thomas just changed the cotangent into tangent instead of making it into sine, cosine, and we deal with 4 things. We will make it into tangent, cotangent, tangent A, tangent B. So let's say I will redo this problem. I still do from right to left. So proof from right to left, right hand side, I get tangent A plus tangent B over cotangent A cotangent B. And then I will rewrite it into, on the denominator only, I change those cotangent into 1 over tangent. So this is 1 over tangent A plus 1 over tangent B. Is it okay? Now we have complex fractions, not so complex, so you can do LCD if you like, right? You can do LCD. I think LCD is actually the best one. From here, let me show you 2 different ways. So I have, this is my second way, but even in my second way, I have 2 different approaches. The one I have here, I will do tangent A plus tangent B, that's the numerator. On the denominator, I create LCD. So that's tangent A, tangent B, tangent A, tangent B. So this is tangent B. This is tangent A. Okay, so I get on the top the big fractions, tangent A plus tangent B on the top. And at the bottom, I have a fraction of tangent B plus tangent A over tangent A, tangent B. And just like before, if I have divided by a fraction, that's the same to multiply by the reciprocal. Multiply by tangent A, tangent B over tangent B plus tangent A. Yeah, but notice that this guy here, which is basically over 1, on the top left and the bottom right, they are actually the same expression. So they can cancel and we get tangent A plus tangent B, which is our left-hand side.
No plus.
Oh, no, no plus, thank you. Yeah, multiplication. Okay. Now, another way to solve or simplify that complex fraction here, another way to simplify this complex fraction, another way is, what happened? Another way is, to multiply, so I have this, to multiply by the total LCD, overall LCD, which is tangent A times tangent B. Such that on the top you will get tangent A plus tangent B times tangent A tangent B over, now notice that what will this guy times tangent A tangent B? That will be tangent B, is it right? Yeah, tangent A will cancel, right? Okay, plus the second term on the denominator, when we multiply by tangent A tangent B, what do we get?
Tangent B.
Tangent B. Now you see that the this guy here and this guy here, actually, the first one should be tangent B. Okay. The first one should be tangent B, and the second one is tangent A. Because the first one tangent A cancels, so I have tangent B. The second one tangent B cancels, I have tangent A. But, well, anyway, that's just the same term with that top one. You see, it's a lot faster if I use this method. That's tangent A, tangent B, which is my left-hand side. And that's the end of the proof. Now, I can show you 20 examples of proving and you learn nothing. What I can suggest you to do when you practice at home, okay, you practice you don't need to actually practice a lot of questions. The number of tricks that are available, actually just those kind of tricks. Multiply by the conjugate. How do you simplify complex fractions like in this question? How do you prove, for example, if it is too complicated, you make it sine cosine, but it, in this case turns out to be quite heavy. Okay, but if you deal with tangent and cotangent only, change them to tangent. If you have tangent and secant only, then you may want to use secant squared equals to 1 plus tangent squared thingy. That relationship will come into play. Okay, and of course, a lot more possible variations. If you want to learn all those variations, by the time you learn the 100th variation, you forget the first 10. You know, so no, don't memorize the variations. Let it flow. Learn to do mathematical manipulation. Okay, yeah, and that's how we actually make you memorize those formulas. Your suggested homework from here will be from 6.5 part B, number 15 to 35. Just do every other odd unless you want to do more. Okay, and then you may want to consider doing number 41. Number 41 is pretty good. Number 41 and 45. Okay, that's the suggested homework. Oh, by the way, I think I want to mention that I post all tests from 419. I didn't post that in the past, but I just posted today. either. You can go to 419. You're looking my website right now, right? Okay, on 419 you can see Precalculus, and I have the Precalculus test. No solution though. Okay, no solution. Yeah, if you want to get the one with solution, then you look further back. And I think I would also like you to realize that since most of the material you do here, half of the material you do here is trigonometry, you can study from my trigonometry material. Okay, from 419, for example, 419 test, Math 241. So you may want to take a look on test 2 or test 3. Okay, maybe test 1. I think test 2. Let's see, test 2. So you may see problems like this, especially number 2 and number 3. Okay, because we will learn radian later on, right? Okay. You're supposed to see graphing this in this test though, but we don't have time, so I will push the graphing part to test 4. Okay, computing inverse function, not yet either. We need to do graphing yet, but when it comes to proofing, you should be able to do that already. So like for example, this number 9 in 419 Math 241 trigonometry. Okay, and study that one, and this guy also. This guy. Oh, this number 11 is the one we just did. Oh, don't you think so? Nobody say anything. Well, anyway,
It looks
I
like it.
see.
I just changed the x. AB becomes xy, and I move it from left to right. Right. Left hand side becomes right hand side. Right hand side becomes left hand side. That's what I do. And notice that I actually used Precalculus question and I asked that in trigonometry. Thomas, you are crazy. No, I'm not, because that's what I learned there anyway. Okay, this question, you may think is that this question is in Precalculus book. It's also happened to be in trigonometry book. Okay, so you can say Thomas crazy by asking Precalculus question in trigonometry class, but on the other hand, I can say I'm being nice by asking trigonometry question in Precalculus class. Okay, because this is in trigonometry textbook. Okay, well, anyway, I hope then, so from fall 19, I think if you go to spring 19, you also see my Precalculus there. Even though spring 19, hold on, spring 19 is something you already posted, huh? Right? Yeah, but there are 6 tests there, so you need to do adjustment. See the topics that we already cover in this class that you should be able to do there. Well, anyway, let me move on to chapter 7. 7.1 is short. I hope that's really short. 7.1 is on radian and degree. Now, 7.1, definition of radian. Definition of radian measure.
You need to share your screen.
Oh yeah, thank you. Thank you. Definition of radian measure. Okay, now we will have a newer definition of angle, and unfortunately, this is the way it will be done in calculus. Okay. No, I don't need this. Let's say this is the radius. Let's say this is the radius. Okay, and there's another radius.
Professor, 7.1 is not included on the exam.
It will be.
It will be up to 7.3. Yeah.
Yes.
Okay. Thanks.
Now, the radian measure that we will be dealing with is the central angle theta here in radian is defined to be theta is equal to, it's defined to be the arc length, the length of that yellow arc, usually denoted by S.
Sorry to interrupt, but the 7.1 it's included on this coming test? No, right?
That's what Nona just asked me. Yes.
Oh. Oh, okay.
And it wasn't me, Professor.
Repeat again.
That wasn't me asking, just to let you know.
Yeah. Nona is the one asking that just now. Yeah, 7.1 to 7.3 still in your this test, Thursday. You learned this already in trigonometry. So we just review it.
Oh, okay.
Okay? Yeah, of course, if you don't learn trigonometry right, then blame that teacher.
No, we have a little bit.
Yeah, you learned this before. Okay, you learned this before. Divided by the radius. So the radian measure is defined to be the ratio of the length, in this case arc length, and the length of the radius. Okay, that's why radian measure sometimes not written. Okay, radian measure sometimes, actually, to be more precise, most of the time not written. Okay, so when we say the angle, let's say we say sine 2, okay, that statement is the same to sine 2 radian. Okay, theta equals to 2, because I don't use any notation, it means it is in radian. Okay, now theta equals to 30 degrees is not the same to 30 without degrees. Okay, with degrees and without degree sign is totally different. Without degree sign, it means it's in radian. Okay, now in this section, the focus is actually on the conversion between radian to degrees and degrees to radian. But let's first see how we will do the conversion. Conversion from the degree to radian, radian to degree. Now we will do as the following. One full circle has a central angle 2 pi. Okay, has central angle 2 pi. Because the circumference, the arc length, is 2 pi r. Let's say, to be more precise, let me go back a little bit. The angle is 360 degrees, right? Okay, the angle is 360 degrees. Okay. The question is, what is that? What is that in radian? What is that in radian? Now we know that theta equals to S over R. So the angle in radian for one full circle is 2 pi r over r. That's how we get that 2 pi. Okay, so the central angle 360 degrees, which is one full circle, is actually equivalent to 2 pi radian. Let me write it down. 360 degrees is equivalent to 2 pi. Now, I don't need to write any radian because once I don't write anything, it means it's radian. Okay. Now, if I divide by 2, and pi will be 180 degrees. Now, to help us with visualization, let's see the following thing. Now, suppose this is my angle in degrees, 0 degrees, 90 degrees, 180 degrees, 270 degrees. Now, we have seen earlier that pi is equivalent to 180 degrees. So what will be 90 degrees in radians?
Pi over 2.
Pi over 2. Now, you can try to visualize that this 90 degree is half of that pi, right? Okay, now how about 45 degrees?
Pi over 4.
Pi over 4, because 45 degree is half of that 90 degrees, right? Now, pi over 30 degrees is 90 degrees divided by 3, right? 30 degrees is 90 degrees divided by 3. Okay, so pi over 2 divided by 3 is pi over 6. Okay, and then 60 degrees is 1/3 of 60 degrees is 1/3 of 180 degrees. So that's pi over 3. Now try to visualize that in picture first. And I hope you can memorize that faster, that pi over 2 corresponds to 90 degrees. Pi over 3 corresponds to 60 degrees. Pi over 4 corresponds to 45 degrees. Pi over 6 corresponds to 30 degrees. Okay, now those are for special angles. Now, how about angles in general? Then we will do the following. Suppose, for example, I want to convert from degree to radian. Suppose I have 40 degrees. What will that be in radian? Then I will multiply by pi over 180 degrees. Pi is equivalent to 180 degrees. But why I multiply by pi over 180 degrees? Because I want to cancel the degrees. Okay, I want to cancel the degrees. In fact, in this case, I can cancel the 0 further and reduce by 2. Then I get 2 pi over 9. Now, because I don't use the degree sign, then it must be in radian. How about if we have 125 degrees? Can you convert that to radian? What will that be? 125 degrees times pi over 180 degrees. Cancel the degrees. I think I will cancel by 5 also. That's 25 pi over 36. I think that's the simplest possible. Okay. Now, on the other hand, suppose I want to convert from radian to degrees. Let's say pi over 5. What will that be in degrees? That will be pi over 5 times multiplied by 180 degrees over pi. That way I can cancel the radian. Okay, in this case, I happen to cancel the pi. Okay.
36.
So that will be 36 degrees. Now, suppose that I have the radian is 2. 2 radian, what is that in degrees? So I multiply that 2 by 180 degrees over pi. Nothing to cancel. That's 360 over pi degrees. Usually we write it that way, but you can also write it this way, 360 degrees over pi. Either way is fine. I like this one. I like this one. Okay, but I cannot mark this wrong. I cannot mark that wrong. Now then, how do we use this? One of the big use of this, especially into the special angles, will be, for example, if I pick question number 32. Number 32, that's on page 496. Page 496, number 32, part A. Cosine 5 pi over 3. Now you may say, oh Thomas, can I convert that to degrees first? You can, but I myself will not though. I myself will not. You can change it to degree and then kill that from the degree. Okay? Yeah, let's say I do it degree. Let me show you how I want you to show the work, even if you make it into degrees. First, if you make it into degrees, that will be 300 degrees. Okay, now the thing is, how do you compute cosine 300 degrees? I hope you don't forget. 300 degrees is in which quadrant?
Third quadrant.
Or
Fourth quadrant, sorry.
okay, and then this is the reference angle.
60.
60 degrees. So in quadrant 4, cosine is positive, reference angle 60 degrees. So that is equals to F. Okay, now this is the old way to do it. If you want to do it this way, fine, I don't mind. Okay, but I prefer this way. I prefer this way. You see right away from 5 pi over 3. 5 pi over 3 is more than 3 pi over 2. 5 pi over 3 must be in quadrant 4, right? Okay, must be in quadrant 4. 5 pi over 3 is in quadrant 4. And then in quadrant 4, cosine is positive. So this will be positive cosine. Now, what is the reference angle? The full circle minus 5 pi over 3. So 2 pi minus 5 pi over 3. That you get pi over 3, which is 60 degrees, that's 1. Okay, this is the way I recommend you to learn. Okay, but if you want to use the yellow one, fine, go for it. Okay, what I don't want you to do is like you do this, like I give you cosine 5 pi over 3, boom, equals to 2 right away. You know, I will ask you why, and I don't want you to tell me calculator. Okay. Now, how about number 32b? Number 32b, that's cosine negative cosine of negative 5 pi over 3. There are 3 ways to do this. The first way, you say, oh, cosine negative is cosine positive. You use property B31. Actually, negative angles, B4, my bad. Not B3. You don't need to write this though. We all know that. Okay, and then from there you go on. Oh, this is equals to 5 pi over 3 is quadrant 4. Cosine is positive. The reference angle is pi over 3, and therefore this is 1. That's the first method. I actually prefer the second method in this case. Cosine negative 5 pi over 3, the period is 2 pi. So negative 5 pi over 3 plus 2 pi will give us pi over 3. So cosine negative 5 pi over 3 is coterminal with pi over 3, which is 1/2 right away. Okay. Now the third method, of course, the primitive method. The third method, guess what? Somebody's so scared with radian, they always change it into degrees. And the reason you will forever be scared with radian, because you dare not face that head on. If you never face it directly, you will never learn it. Okay? And you can see those students in my Calc 2, they wonder why they don't do well, and I wonder why they don't memorize those angles in radian. You know, imagine when they did if you happen to learn integration before, they do integration from 30 degrees to 60 degrees. No, it's not doable. When you do integration, it has to be real numbers. It cannot be degrees, ever. Not doable. Okay. Yeah, but at this level, if you want to do it this way, fine. But don't blame me if you don't have enough time later on. Okay. Yeah, because then you need to convert that to degree first, right? In 2 days, of course, I understand if you need to change it into degrees. Okay, but in long run, don't. Okay, in long run, try to shorten that. Okay, we did the 5 pi over 3. If you take a look for question C, that's actually sine 5 pi over 3, right? Okay, so if you ask me to do this and I want to stick with the radian, then I ask myself 5 pi over 3 is in which quadrant?
Fourth.
In quadrant 4, so sine is negative there. What is the reference angle? Pi over 3. So this is negative sine pi over 3, which is negative radical 3 over 2. Let's see, for example, number 38. Number 38, part A. Secant 7 pi over 4. How will you do this? Well, I don't know the value for secant. Let me change this into 1 over cosine. Okay, and then there I see.
Number 3.
Repeat again?
You didn't do number 3.
I didn't do number 3.
Yeah. This on the screen. You didn't finish it.
Oh, I don't need to finish. You can just do it yourself. That's why I use the dot.
Professor, for part C, the sine of 5 pi over 3, if we add that to 2 pi, doesn't it give us 11 pi over 3?
Yeah, 11 pi over 3, so what?
So shall we write negative sine 11 pi over 3?
No, no. Well, if you add 2 pi, you don't change the positive negative. If you add 2 pi, you don't need to change the plus minus. It's coterminal. But I don't think you want to add 2 pi though. This is not negative 5 pi over 3.
So if it's negative, that's the only time we add it to 2 pi?
Well, if it is negative, okay, one way to do it, it's not the only way. One way to do it, you find a coterminal. Coterminal means, let's say, where's my circle? So negative 5 pi over 3 is actually going this way, right? So let's say this is the angle. Now, yes, this is the terminal side. Now that terminal side corresponds to the same angle here.
Oh, okay.
Okay, that's what we meant by coterminal. Okay, these two angles are coterminal, means they share the same terminal side. Now, if they are coterminal, then all the trig functions have the same value. All the trig functions have the same value. By the way, the question earlier was sine 5 pi over 3. Can I add 2 pi? You can always add any angles by 2 pi to get the terminal sides. But 11 pi over 3 is not one of our special angles, though. It's more than 2 pi. It's more than 2 pi. In fact, if I ask you sine 11 pi over 3, your first step will be make it in subtract by 2 pi to get sine 5 pi over 3. And then from there you go on. Okay, this will be cosine reference angle pi over 4. That's 1 over radical 2. So this is radical 2. Yeah, basically for secant, cosecant, and cotangent, you need to rewrite them in terms of sine, cosine, tangent. And then from there you go on. Okay, let's take a break. We come back at 6. Let's say we come back at 6:05. Okay, let's continue. Number 36 BC, 38 BCD. Number 38B, simplify cosecant. Oh, is it B or C? Yeah, cosecant negative 7 pi over 4. That's 1 over sine of negative 7 pi over 4. Now, what do you do from here? You have many ways. Just give me the method, the procedure.
Reference angle, coterminal angle.
Coterminal is? You add 2 pi, that will be pi over 4, right? Yeah. So this is
45.
1 over square root of 2, and the answer is square root of 2. Now, somebody else may do it another way. They say, oh, you know what? Can I do negative angle first? Fine, negative angle. So this is negative sine 7 pi over 4. That's also okay. And then this is equals to 1 over negative. And then sine 7 pi over 4. 7 pi over 4 is quadrant 4. Right? So sine is negative. And the reference angle is pi over 4. So you see that the negative cancels, right? And I end up with 1 over sine pi over 4, which is the reciprocal of 1 over radical 2. That's radical 2 anyway. So yeah, this one question can be done at least with 2 different ways. Okay, you use the coterminal approach or negative angle approach. Okay. Number 38C. Number 38C, tangent of 7 pi over 4. In quadrant 4, tangent is negative. Reference angle is pi over 4. So this is -1. Part D, cotangent. Oh, do I read the question right? Oh, cotangent negative, cotangent -7 pi over 4. That's 1 over tangent of -7 pi over 4. I think I would just do the coterminal. So that's 1 over tangent pi over 4, which is just 1. Okay, now that's for 7.1, mainly on conversion from degree to radian, radian to degree. But then on the top of that, you more or less need to memorize the special angle in the first one period, instead of only in the first quadrant, also in special angles in radian in quadrant 2, quadrant 3, and quadrant 4. Okay. You know what? Let's do this thing. Let's do this thing to help you picture that. Let me go back. I remember I have that file. Where did I put it? The file for the unit circle. Where's that? Okay, where did I put it? Okay. Give me a second. I wonder if you remember these. You remember this? Yeah, try that. So this is 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. This is 180 degrees, 120 degrees, 135, and then 150 degrees. Now, then this space here is for the radian. Let me use blue color. This is 0 radian, pi over 6, pi over 4, pi over 3, pi over 2. This is pi radian. Okay, now how about these here? What will they be in radian? What will they be in radian? And use your visualization. Use your visualization. For example, this guy here, this is pi plus pi over 6. From pi over 6, you add 180 degrees, right? Okay, so pi plus pi over 6 will be
7 pi over 6.
7 pi over 6. Okay, this guy here corresponds to pi over 3 plus pi. That's 4 pi over 3. That way it's faster, instead of like you convert, oh, you know what, this is for 240 degrees, and then you use that multiply by pi over 180. That will be slower. That will be slower. Okay, that will be slower. Now you may say, Thomas, can I just use calculator? Not really, because when you use calculator, your calculator will change pi into 3.148, blah, blah, blah. So you will not see a nice number. Okay, don't rely on calculator too much though. Okay, yeah, don't rely too much on calculator. Now, and then let's say this one here, this is 330 degrees. You see that's 30 degrees less than 2 pi, 30 degrees less than 360. So that will be pi over 6 less than 2 pi. This will be 2 pi minus pi over 6. Okay, that's 12 minus 1, that's 11 pi over 6. Okay, so try to kind of like memorize it that way though. Now, that's not only for this class, but especially for later on. Okay, especially for later on. Now let's go on to 7.2. Give me a second. Give me a second. Peter, don't play here, please. I'm sorry. Now, 7.2. In 7.2, we will learn three things. What are those things? The first one is arc length. The second part is sector area. The third part is linear and angular velocity. Okay, now somewhere in between, let me call that 2B. Later on, I will teach you what we call segment area. Yeah, I don't see this topic being covered in other textbook, but our textbook actually cover it. Okay, other textbook can easily cover it too. Okay, now arc length. We have known that the arc length S divided by the radius give us angle theta. Okay, so theta in radian equals to S over R. The theta has to be in radian. Okay, now then using the same formula, we will get the arc length equals to theta times R. That's it. Don't forget, the theta has to be in radian. Okay, the theta has to be in radian. So the length here is equals to the theta in radian multiplied by the radius. Now, what is a sector? A sector is the pizza. This is the sector. Like imagine if you have a pizza, okay, then the area is the blue region here. Okay. Now sector area is equal to 1/2 theta R squared. Sector area is 1/2 theta R squared. If you call this the proof for the arc length, then how about the proof for sector area? Proof: sector area is proportional to its central angle. So if I take a look on that figure there, the sector area, the one that I marked with blue color, the sector area divided by the central angle is equal to the area of the circle over, I'm sorry, I think I used the wrong notation. It's not supposed to be S. Sector area is A with that pizza. Okay, the area of the sector is proportional to the central angle. So area of the sector divided by the central angle should be proportional to the ratio of area of the circle to 360 degrees, or in radian, that's 2 pi. Because my theta should be in 2 pi. My theta should be in radian. Okay. Now we know that area of the sector over the central angle of that sector equals to area of a circle is pi r squared over 2 pi. You see that I can cancel the pi, right? So the area of the sector now, sector area, is equals to 1/2 theta r squared. Okay, that's the formula. Then you have to memorize. Now, I said you have to memorize, but I have to be honest with you. On your test this Thursday, I know some of you may open your book, and I assume you open your book. Okay, I just hope that if you need to open your book, you don't get occupied with studying during the test. That's one. And second, you know what you look for. Okay, what you don't want to happen is you open the book and then you spend 2 hours in seeing which section this question should be tackled with, and of course you don't have enough time. Okay.
Good question.
Uh-huh.
When you say that the sector area is proportional to the central angle,
Uh-huh.
you mean by division, by multiple, or it doesn't matter? It just
proportional. The proportional means the ratio has to be constant.
Oh, okay. The ratio is constant.
Yeah, the ratio is constant. So even when you look at this, even when you look at this picture here, right? Mm-hmm. Okay, and suppose I pick another sector, different size. Okay, let's call this alpha here. Mm-hmm. Okay, then the area for the blue sector and the area for the green sector, the area for the blue sector, the area to the green sector should be equal to theta over alpha.
Yeah. Okay.
The larger the angle, the larger the area, right? If you double the angle, then the area will be double too.
Yeah.
Does that make sense?
Yeah.
Okay. So when I try to develop the area of a sector, I actually compare that with the full circle. Mm-hmm. Okay.
Yeah.
Now, actually, I want to go on a bit further. Notice that theta r equals to s, right? I mean, we know it from up here. Theta r equals to the arc length. Okay, so the area of a sector can also be said to be 1/2 s r. So if I have a sector, okay, the area of this sector is equal to the radius. This is radius, this is radius, this is radius. You can pick any radius, multiplied by the arc length, the s. Now notice that this formula mimic very closely the area of a triangle. Okay, I think that's not a coincidence, but it's irrelevant to say right now. One of the big use of sector area is actually on finding the area of a paper cup. Let's say I have a paper cup. I have a cup, let's say. Okay, and then let's say the radius of that cup is 5. Okay, and then the slant here, the length of the slant is, let's say, 7. Now then the question is find the area of paper cup, paper being used. Now, here's the thing though. Suppose I cut this paper cup along one of the slant radius. If I cut it there, okay, and then I flatten it, then it will look like this. It will look like this. Maybe like this. Okay, in which the 7 will go here, right? That's the 7. That's the 7. Now the thing is, what will this be? What will that be? Now notice that the blue part here is actually coming from the circumference of the base of that cone. Right? Now the circumference of the base of that cone is actually 2 pi r, right? Which is 10 pi. Now then, how about the area of this sector? This is a sector, if you think about it, right? That's a sector. What is the area of that sector? Area of that sector is equals to 1/2 arc length times radius. That's 35 pi. I use this formula. Okay, that's one of the use. Well, anyway, don't worry too much about that. You will see that, supposed to have seen that in geometry though, but we don't take geometry class at WLAC College. Okay, but then it will come back to you in Calculus 3 at least. But by the time you are in Calculus 3, you basically just memorize this formula already. So again, don't worry. I'm sorry, don't worry about that right now. Example. For example, suppose I have a sector whose angle is 70 degrees and the radius, let's say, is 6. My question is, so the theta equals to 70 degrees, the radius is equals to 6. The first question is find the arc length, find S. And then second, find the area of the sector. The first thing we need to do is we need to convert this into radian first. Okay, never attack that in degrees. So theta equals to 70 degrees times pi over 180 degrees. That's 7 pi over 18. Now then, when I apply that to the arc length, that will be theta r. 7 pi over 18 times 6. So that would be 7 pi over 3. So let's say the r is actually in inches. Let r be in inches, then the arc length will be in inch also. Okay. How about the sector area? the sector area will be 1/2 theta r squared. Or if you want to use part A, you can also use 1/2 S times R. Okay, either one. That will be 1/2. The theta is 7 pi over 18. And then the R is 6 squared. Oh, that would be 7 pi half. Because that's 7 pi times 36, but at the bottom is also 36, right? So the area will be 7 pi, the unit will be square inches. Okay, you want to do 1 or 2 problems from the book? Okay, Thomas type of question, part C. Find the perimeter of that sector. Now notice that the perimeter of that sector is the arc length plus twice the radius. Okay, so distinguish the arc length, which is only the crust of the pizza, only the crust of the pizza. Okay, the perimeter, you need to add to it twice the radius. Okay, so that will be the arc length plus twice the radius. That will be 7 pi over 3 plus 2 times 6. So 7 pi plus 12 times 6, 36 over 3 inches. Okay, where the S is this part here, and twice the R is the yellow part. Okay, now that's 2A and 2B. That's 2A and 2B. Part 2, I'm sorry, that's 1 and 2. Now 2B is segment area. Segment area. Now segment area, a segment is the pizza. Segment is a pizza. Sorry. A pizza minus the triangle. So let's say this is the pizza and this is the triangle. Okay. Now this is what we call the segment. This part here is the segment. Okay, that part is a segment. Now, then, if the radius is r and the central angle is theta, then what is the area of that segment? Area of segment. The one in yellow color. That will be the area of the sector minus the area of the triangle. Right? Can you see that?
Nope.
No?
Nope.
No? Okay, this segment here.
See what that is. Is that like a part of a circle on top of the triangle?
Yes, it's basically the whole pizza.
Mm-hmm.
Basically the whole pizza. The whole pizza minus the triangle. This is the whole pizza. If you subtract the triangle, then you will get the yellow color.
I see.
Right? Okay? So, now the thing is, the sector area, we already learned earlier, that's 1/2 theta r squared. That's the area of the sector. But do you remember the area of the triangle?
Have base times height.
Yeah, but we don't have base, we don't have height here, but we have theta.
Half r squared sine theta.
In this case, yes, half r squared sine theta. Okay, the formula for the area of a triangle, if I have two sides and included angle, the area is 1/2 a times b sine theta. Remember that? 1/2 times the product of two sides times sine of the included angle. Remember that?
Yeah.
Okay, now then, that's actually the formula, but if you want to factor out 1/2 r squared, then you will see inside theta minus sine theta. That's the area of the segment. Okay, now how useful this formula, as I remember, not really useful. Okay, it's not really, I mean, we don't see that a lot, but our textbook have a question as the following. Our textbook has this question here. Our textbook has the following question. Suppose I have a central angle 120 degrees. So approximately like this. This is 120 degrees. The radius is 3 meters. And find the area of this sector here. Find the area of that sector. The area, I'm sorry, the area of that segment. The area of that segment will be the sector area minus the area of the triangle. But don't forget, we never deal with degrees directly, especially in those formulas. Okay, so I need to change first. 120 degrees is what radian? $60 degrees pi over 3. This is twice of that. So this is 2 pi over 3. So the area of the sector will be 1/2 theta r squared minus 1/2 r squared sine theta. This is 3 pi. The 2 cancel, 1 over 3 cancels, minus 4.5 sine 2 pi over 3. Sine 2 pi over 3, that's 120 degrees. Well, anyway, the reference angle is pi over 3. Sine pi over 3 is radical 3 over 2. So that's 3 pi minus 2.25 radical. That's the area. And in your test, if I ever ask you this question, I think I will ask you this question. It should be a Mickey Mouse question. Then just leave it like that. Don't use calculator. Okay? Don't use calculator. Just leave it like that. Now, the third part from this section is on linear velocity and angular velocity. Linear and angular velocity. In the textbook that we use at SMC, they call that speed instead of velocity. It's supposed to be velocity, by the way. Okay, not speed. Angular velocity, linear velocity. Now, linear velocity is the same to the speed or the velocity, the definition of velocity we have before. The linear velocity used to be denoted by v for velocity. That's equals to the distance traveled over time. Now, however, the distance that we talk about here refers to the distance traveled on a circle. Okay, so the S here refers to the distance traveled on the circle. So, going back to this formula, phi is S over t, while angular velocity refers to omega, that's notation, omega, that's the angle traveled over time. So omega equals to theta over time. In this figure here, oops, in this figure here, it refers to the angle traveled over time.
Can we use S instead of D?
I use S.
Oh, okay.
Yeah, I use S.
They're the same thing.
They're the same thing, basically. Yeah, they're the same thing. The emphasis S here because it actually refers to the arc length. Mm-hmm. Okay, so you have these two formulas to know. Okay, but actually more things we can say. Notice that, let me use another color. Notice that S is actually theta R, right? While at the same time, theta over T is
W.
Omega. So linear velocity is actually angular velocity times radius. Okay, so if I combine these two formulas, I get this linear velocity equals to angular velocity times radius. Okay, let's do problem. For example, I pick question from the book. Let's say number 14. Number 14 on page 502. We have 15 revolution per minute. Oh, actually, this is revolution per second. Okay, and then R equals to 20 centimeter. Now, 15 revolution per second refers to actually omega. That's a speed. That's a speed. Now, one revolution, what is the angle?
2 pi.
2 pi. So this is 15 times 2 pi radian per second. Okay, so this is 30 pi radian per second. Now again, the question part A, what is the angular speed? In radian per second. Oh, I answered that already. That's 30 pi radian per second. That's almost always what you will do first when I give you revolution per second or revolution per minute. Okay, RPM, by the way, stands for revolution per minute. This is revolutions per minute. Not radian per minute, not radian per minute. That's revolutions per minute. Okay, maybe I kind of highlight that. That's for part A. Part B. The linear speed in units of centimeters per second. So phi equals to omega times R. That's 30 pi times 20. That's 600 pi centimeters per second. part C of a point circumference of the wheel, of a point halfway between the center and the circumference. Oh, so for part C, what is the linear speed if the radius is 1/2? So imagine if you have a wheel. So let me tell the stories even more. Suppose you have a wheel, okay, a tire, okay, and the angular speed is omega is 15 revolution per second. Okay, now knowing that the radius is 20 centimeters, then what is the linear speed? The linear speed, as we computed earlier, that will be 600 centimeters per second. Now, part C, they changed the question. What happens if you have the same angular speed, however, your radius is only 1/2? Okay, so if one guy moving here, right, moving along this path, okay, with the same angular speed, then the point will be moving from here to here, right? Now the question is, what is the relationship between this linear speed when you halve the angle?
Times 2.
Repeat again.
We're going to multiply the linear speed by 2.
Actually, you divide by 2. Yeah, because the radius is half, right?
Okay, yeah.
Yeah, the radius is half. Okay, so this is 30 pi times 10 instead. That will be 300 pi centimeter per second. Okay. I really wish I have time to talk about something else.
So when the angle is
the angular speed stay the same. The angular speed still 30 pi radian per second. But because the radius is smaller, then of course the linear speed is smaller.
Are they moving at the same speed or something?
They're moving at the same angular speed. Yeah, so the question in part C is find the linear speed in centimeter per second of a point halfway between the center of the wheel and circumference.
I see.
Okay, so imagine if you have this. Imagine if this is your paddle. You are paddling, right?
Mm-hmm.
Okay, and this is kind of like you put a marker here. You put a marker here. If you move at the distance of s here, then if the marker is only halfway, then the distance traveled by that marker will be only half of that s.
Okay.
You see? Okay. Yeah. I would really, I just don't have enough time. I would really like to talk about this. This has something to do with planetary motion, though. The planetary motion. Let's say, I do it super fast, okay? Let's say this is the sun. Okay, now suppose you have two, you have the Earth, and then let's say you have Jupiter. Yeah, let's say you have Earth and Jupiter. Now, if they move at the same angular speed, then and they are linear here, then if they move at the same angular speed, then when the Earth is here, the Jupiter should be there also, right? If they move at the same angular speed. But notice that the Earth will be moving slower linearly compared to when Jupiter moves.
That's what I was talking about.
Yeah. Okay, yeah, why? Because the distance from the sun to Jupiter is further, right? So to catch up with the angular speed that the Earth has, then Jupiter should be faster. Even though in reality that's not true. In reality, the angular speed are not the same. Okay, in reality, the angular speed is not the same. As I know, the further you are from the sun, the slower the planet will move. But honestly, I'm not sure. I'm not sure. Don't quote me on that one. Okay. That also gives the issue as the following. Now, this one is something I would like to talk about. Imagine if you have a fan, the one that you use to pull you down. Okay. Yeah, the one that you use to pull you down. Now, let's say you want this fan to actually move super fast. So you want the omega to be, let's say, 1,000 revolution per second. I think that's really fast, right? I think that's really fast. That's basically 1,000 times 2 pi radian per second, right? That's 2,000 pi. Now, imagine if my fan has a very big radius. Imagine if my fan has a very big radius. Let's say the radius is, do I want to make it super big? No. Let's say my R is, let me make it small for now. Let me make it small for now, 1 meter. Okay, so the linear velocity will be 2,000 pi meter per second. I think that's not too fast, right? I think that's not too fast. But imagine if I do the following crazy thing. Okay, imagine if I do the following crazy thing. Imagine if I make the angular velocity a lot faster, let's say 100 times faster. So this will be 100 times faster, is it right?
Yeah.
Okay. Plus, on the top of that, the radius, instead of 1 meter, I make it 1 kilometer. I make it 1 kilometer. So my linear velocity right now is 200,000 pi kilometers per second. Do you know what's wrong with this? Okay, let me tell you why it is impossible to do this following thing. Because if this really can happen, then the tip of this fan, it's a very big radius, right? Okay, it's a very big radius, 1 kilometer. Imagine if you have a fan whose radius is 1 kilometer. Okay, and that fan is actually moving so fast, so freaking fast. Okay, now the tip of this fan moving so fast such that the speed is actually faster than the speed of light.
That's faster than the speed of light?
Yeah, the speed of light is only 180,000 kilometers per second.
Okay.
Okay, now, so when people designing the jet, you know, the not the propeller, when they design the jet for Boeing, for example, you see, yeah. Right? Okay, now the fan here is actually moving very fast though. It's moving very fast. Okay, now with the radius they have, okay, they need to be aware that it is possible that, no, it's not possible, it won't be that fast anyway, but at such a high speed, when the tip of this fan actually turning so fast that it will heat up super high. And the purpose is actually the fact that the fan needs to move super fast so that they can condense the air fast enough to push the plane forward. You see what I mean? Okay. Okay. So now the thing is then, why can't they make the jet, let's say the engine, to be even larger, for example? Okay, it has something to do with the linear velocity. Okay, at some point the linear velocity is so high that it heats up so fast and it may burn instead. Okay, at that point it is possible that whatever metal you use, it will burn. Okay, and we of course we don't want that to happen. Okay, it has something to do with the material you use, what is the melting point. Okay, that's 7.2. You may wonder, what do we do in 7.3? 7.3 basically repeating what we did in chapter 6 in 3 minutes. Is it possible? With Thomas, it is possible.
Well, we don't mind waiting longer.
Huh? What?
We don't mind waiting longer.
Okay, let's see. What do we see in 7.3? For example, I picked number 48. Number 48, the question is proof. Proof cosecant t equals to sine t plus cotangent t times cosine t. Notice that when we learned to prove earlier, it actually has nothing to do with the fact that the angle is in degrees, right? Okay, so we can prove this even though the t is in radian. You just do it the same way. Okay, see section 6.5b. Okay, how about number 8a, secant 7 pi over 4. This is done in 7.1. Right? At that time we did, secant is 1 over cosine, right? And cosine in 7 pi over 4 is in which quadrant?
Third.
Huh?
Third or fourth.
The 4 is more than 1.5 pi, right? The cutoff for quadrant 3 and 4 is 3 pi over 2, which is 1.5 pi. Okay, now this guy is more, it's 1.75 pi, right? So it's quadrant 4. Cosine is positive in quadrant 4, reference angle is pi over 4. So this is 1 over radical 2. That's radical. Okay, and you will see that nothing really new here. Nothing really new here. The suggested homework from 7.3, you will see this is just 7.1 and 7.2 put together. Number 1 to number 7, and then why not doing more proofing? Number 47, 49, I think is good. 51, 3 is good enough. Okay, for 7.2, your suggested homework is 7.2. Suggested homework will be, it's really just to train yourself using formula 1 to number 5, number 9, 11, 13, 15, 17. That should be good enough. Okay. So again, I hope you see that 7.3 is just repetition from 7.1 and 7.2 put together. And in 7.1, the new one is basically converting. Okay, you need to know how to convert that to radian, from radian to degree, and then computing the trig function of spatial angle in first or second or third or fourth quadrant. And then in 7.2, you use theta in radian to find arc length, sector area, segment area, and then linear velocity and angular velocity. Okay, that's where I will stop. On Thursday, what time your test will start?